Hello everyone. In this video, I'm going to talk about integer programming. So if we have a LP problem, we need all the variables or part of the variables to be integers. Then we say it is an integer programming problem. So if we need all the variables to be integers, it's called a pure integer programming problem. Otherwise, it's called a mixed integer programming problem. So today we are going to deal with pure integer program, and the method what we are going to use is called a cutting plane method. So now let's start talking an example. Here we consider LP problem as a minimization problem, but if we simply change this to be maximization, just turn the z prime equals to minus x1 plus 3x2, then we can use simplex method, build up an initial tableau and solve it to find. Here is the final tableau, and from this final tableau you can easily to see that we have x1 as non-basic variable, so x1 equals 0, and x2 is a basic variable on the second row, and its value is 15/4. And the objective function has the value 45/4, but it is the value for z prime. And the original problem, we should have z equals minus 45/4. So until now, we haven't discussed that variables should be integers, right? Here, you just know that x1, 0, that's integer, but x2 equals 15/4, which is not an integer. You probably want to say, okay, and x2 equals 15/4, that's a 3.75, which is very close to 4, right? What if we choose x2 equals 4 to say that's the optimal solution for integer program? Actually, it doesn't work. If you look at this graph, because we have only two variables, we can draw the feasible region, that shadowed area, right? And you could see 0, 4 is not in the feasible region. If you back to the LP problem, you could see that if we choose x1, 0, x2 equals 4, and the second constraint failed, you could see that the left side of the constraint is 0 plus 4 multiplied by 4. That's 16, which is greater than 15, right? So here, that 0, 4 is not in the feasible region. And you could also see that there are lots of integer points in the feasible region. For example, that 0, 1, 0, 2, 0, 3, and 2, 2, or 1, 3, or in the feasible region. Then which one we may reach the optimal solution for the integer program, pure integer program? Here, of course, you can evaluate all the points in this problem, but if we have a large feasible region or if we have an unbounded feasible region, you don't want to do it, right? So here we are going to use graphic solution to work out it. We are drawing isomorphic lines. So we let the objective function have a value p, then we can get that x2 equals half x1 minus 1 or 1/3 p. And you know, on these lines with different p value, you could see that the p keep the same. So that means the value of the objective function have the same value on each of the on the at the points on each of the line, right? So what we say is that the p value won't change on each of the lines. Okay, so here we are drawing these lines. You could see that when we have the as a profit lines, and that because it's a minimization problem, so when we draw it, it first touch to 0, 3.75, so that's the optimal solution for the LP problem, but not the LP problem with all the variable to be integers. And then we have to keep going. And the first point, integer point, the as a profit line touch is the 0,3. So this one is the 0,3 is the point we are looking for. The value of z is -9. So in this way, we get our optimal solution for the pure integer programming problem as z equals -9 at 0 over 0,3, right? x1, 0, x2, 3. In general, how may we solve it? This is something we are going to discuss. So here we consider an LP problem, and in standard form, and we also want those variables to be integers. Here we consider all the constant entries are integers. Now what we do is the same as what we did in the example 5.1. We first solve the problem by the simplex method if we can, or we use two-phase method, or we use bigger method to solve the problem. Just at the beginning, we don't even consider those variables should be integers. Okay, and then once we get the result, if it is integral, and then we're done. If some of them are not integers, then we just simply choose one, and we add a new constraint to cut off the non-integral part of the solution. Okay, if we have to keep doing it until we reach an optimal integer solution. Okay, so this is what we call the cutting plane method. So now let's just assume it more general. We suppose that when we work out the LP problem with simplex method, then what we want to do is we found that on the ice row that xbi is not an integer. That means the basic variable has a non-integer value. So here we just consider it as the ice constraint. We just simply write down the ice row and as an equation. That's what we call ice constraint. So that we use that I to represent which row in the final tableau, and then the j represent this is ti1x1 plus ti2x2 plus tij xt plus finally plus ti n xm. Oh, here xb, as we said, it is the value of the basic variable in this ice row, right? So here we use, if we use that tij with square brackets represent the largest integer, which is less than equal to tij. Okay, so largest integer less than equal to tij, we replace all of these tij, okay, because that this one is less than equal to tij. So in this way, we have the equation 2 becomes an inequality. And since such a value on the left side is also integer, because we need all the variables x to be integers, so that on the left side it is an integer. And the not just the integer which is less than equal to bi should be greater than or equal to the integer on the left. So in this way, we have an inequality that all of them are integers. And then we add a slack variable ui on that, and then we have a new equation. And as we have integers, ui as an integer between two integers, then we may say ui is also an integer. And then here we consider that we know Tij is the largest integer of Tij. So we just use Gij to represent the fractional part of Tij. So therefore Tij equals the largest integer which is less than Tij plus the fractional part Gij. And the same as we have xbi as the largest integer less than bxbi, then plus the fraction part we denote it as fi, then that is xbi. So, well, that you understand that Tij could be integer. So in this way, Gij could be 0. So here we have Gij is between 0 and -1, and Fi is between 0 and 1, because at the beginning we already assumed that xbi is not an integer. If xbi is an integer, we don't have to work on that, right? So now we use equation 3 minus equation 2, collect those variables. You could see this one, and the equation 3 minus equation 2, we can get that all the xj has coefficient minus gij, and we keep that ui, and the right side is minus fi. And this equation actually is what we called the cutting plane for the ith row. Okay. Now what we do is we just put it into the final simplex tableau and work out it. Now let's back to the example 5.1. As you remember that x2 is the one we need to work with. The second row in the final tableau of x2 is, if we back to here, you could see that is, you see that the second row is a half of x1 plus x2 plus 1/4 s2 equals 15 over 4, right? Now we take it as the second constraint of the example 5 in its final tableau, and now we just follow what we are working on at. So we have, that's the equation 2. That's the equation 2. And then you could see that because it's on second, this is the second constraint. So I equals 2, and the coefficients before x1 is t21. So t21 equals half, and t22 equals 1. There's no s1, so t23 equals 0, and t24 equals 1/4, and the xb2 equals 15 over 4. As we know, Tij, the square brackets Tij denote the largest integer, which is less than Tij, right? So for instance, we could say the largest integer which is less than half is 0, the same as this one. The largest integer less than 1/4 is also 0, right? And the largest integer which is less than 15/4 should be 3. But here, pay attention. If we want to find the largest integer of -15/4, that is negative what? negative 4, because negative 15 over 4 is negative 3.75 is greater than equal to negative 4 less than equal to minus 3. So in this way, the largest integer, which is less than negative 15 over 4, is minus 4. Now, here, what we follow this one. So here, with this one, since the largest integer less than Tij, and then we have that make all the coefficients before each variable to be largest integer less than the coefficient, right? And which is less than x bti. So here we have this one equal this one, largest integer less than 15 over 4 is 3, and those largest integer less than half or 1/4, that's 0. So in this way we can keep that right side 15 over 4. We know x2 is less than 15 over 4, like what we have this the equation. And then we just put that in this way we also have that x2 less than equal to 3. And then we add a slack variable here, x2 plus u1 equals 3. And since b2 is 15 over 4, not integer, so we just work out this with that tij, with gij. So let's look at this. The largest integer less than tij. In this way, we work on each of them. For t21, we know t21 largest integer of t21 is 0, so 0 plus half is half. So that t21 equals the largest integer of t21 less than t21, and plus half equals t21. And we also have this the largest integer less than t21 plus 1/4 equals t24, and the largest integer of xb2 plus 3 over 4 equals 3 plus 3 over 4, that's 15 over 4 equals that xb2. So in this way we can work out that G21 actually is half, G24 is 1/4, and F2 is 3 over 4. Here I have to mention this. Sometimes we might have a negative sign before the variable. So for example, if we had t21 equals minus half, then we know that the largest integer of t21 should be largest integer less than t21, that is less than negative half is minus 1. So in this way, if we want to express it as the form like largest integer less than tij plus gij equals tij, then that is largest integer less than t21 plus half equals t21. And here, this leading to g21 equals half. So whenever the coefficients before the variable is negative, you have to pay attention there. Okay, so now once we have that G21, G24, and F2, then we can work out the cutting plane constraint. Just minus G21 and x1 minus 1 over 4 s2, and plus u1 equals negative 3 over 4, because G21 equals half, G24 equals 1/4, right? So this is the cutting plane constraint for the example 5 in the final tableau. So now what we do is we bring it into the final tableau of the example 5.1, and then you could see here we have infeasible solution because u1 equals minus 3/4, and all the entries in the objective row are non-negative. So in this way, it is what? It is in optimal case but infeasible. So we use dual simplex method to restore the feasibility, and once we work out it, and we could find out that the final final tableau is like this. So this gives us x1 still non-basic variable has a value 0, and x2 equals 3. So this actually is the same as what we did in graphic solution. The optimal solution for the example 5.1 is z equals minus 9 at x1 equals 0 and x2 equals 3.